So in this class we will be seeing the naive Bayes classifier in a much formal way. In the previous class we saw what is actually the Bayes classifier. The Bayes classifier is a kind of classifier that uses this Bayes rule in order to calculate the probability. The Bayes rule calculates the probability for a given variable for a particular variable given another variable. So in our text classification problem we are interested in calculating the probability of a class Cj given a document di, right? So given a document di, so suppose di is a test document, so we are interested in finding the probability of different classes. So the classes may be c1, c2, c3 dot 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 cj. So we are interested in finding that particular class which has the maximum probability given the document di, right? So this argmax is a function that says that a kind of function, so you can assume it like this. It says max, it finds actually max of all these probabilities, p of c1 given di, p of c2 given di, and p of c3 given di, and so on. And since we are doing argmax on c, so it will, this maximum means that I am trying to maximize the probability formula on the basis of c. So this max will return that value of c which has the maximum probability among these, right? So this returns me a c, that is called as a c. MAP is actually maximum a posteriori. So maximum a posteriori is that probability which maximizes the posterior, right? So this, in this formula we call this as the posterior probability. Posterior probability, this is called as the likelihood, and this is called as the prior, right? So maximizing this probability is called as the maximum a posteriori, and maximizing this probability, maximum likelihood, is called as the maximum likelihood estimation, right? So we are trying to maximize p of c given d, so we are getting that class that will be c map, that is maximum a posteriori. So now putting again p of c j given di can be expanded using the Bayes theorem here, that is equal to p of d given c multiplied by p of c divided by p of d, right? So this is actually the likelihood, this part is the likelihood, and this part is the prior, and this is di given cj, this is again p of cj, and this is di. So we will be doing again this same thing will be done for all these probabilities. So it will be p of di given c1 dot p of c1 divided by di. Then for the next probability we will be using p of di given c2 dot c p of c2 divided by di. So in all these probabilities, when we expand these into the Bayes rule, we see that the denominator is always the same. So denominator does not make any effect while calculating the probability. So we can ignore this denominator, and the final formula for calculating the argmax or maximizing this probability in order to calculate the maximum value, in order to calculate a c value or class value that maximizes this p of d given cj dot p of cj, is only this numerator part, right? So we can leave out the denominator because this does not make any effect into while calculating these different probabilities, as this p of di will remain the same for all of these. So we need not be just applying an extra computation and calculating every time unless and until it is required specifically by some kind of problem. So for just prediction of the maximum prediction of the class to which the document belongs, we can directly use this formula, right? So this MAP is actually this argmax of the class that belongs to set of classes P of di given Cj dot P of Cj, right? I am taking this P of di given Cj as this document di may belong to again a set of documents. So D, maybe d1 comma d2 d1 d2 d3 and dot 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 dm. So this document may be any among these documents or any kind of some new document also, but this Cj is given these fixed class. We can have C1 C2 dot 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 Cj and Cn, right? So this Cj is among these fixed set of classes, but di is not fixed. Di can also be a new one, right? So now when we say that this is di given Cj, what does it mean? It means that I am taking this any document, particular document from, suppose I take this d3 or I take this d2 or I take this d1, any document. So this document will have some kind of features. Suppose it is having n features. So each document is having n features. As we discussed in the previous class, what kind of features we can take, we need to decide prior to performing the classification. So suppose there are n features, so we can write this document di is actually composed of n features. So di can be replaced by x1 x2 x3 dot 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 x of n. So this di can be now decomposed into n features. So this formula P of di given Cj can be now written as P of x1 dot P of x2 dot P of x3 dot 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 xn of I. So we can write this again subscripting this I as this x1 belongs to the document I, and this is we are doing for a particular class Cj. So while writing argmax, we don't need to specify specifically Cj, but for more clarity I am specifying it as a Cj that belongs to set of classes, right? So now we can expand this P of di given Cj as P of x1 dot 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 xn given Cj dot P of Cj. Right. Now these are actually the document, these are the features that are present in the document. But if we now see these features, so these features are actually converted into numerical values while putting it into the classification algorithm. So we get this kind of feature matrix, which for each document. So we discussed earlier also that suppose these are the features, this is x1, this is x2, this is x3 dot 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 x of n, and these are the documents d1 d2 d3 and so on dm. So for each document there will be some numerical value of x1, suppose it is 4, it is 2, it is 7, it is 21, and we can have some kind of similar values for d2. Is suppose 0, it is 8, it is 3, it is 9. Right. So this P of x1 dot 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 xn is actually we will be putting x1 is equal to 4 here for d1, x2 is equal to 2, xn is equal to 21 given some class Cj. Right. So these values are actually very this we will be taking the combination of x1 up to xn. So when we represent this x1 as x up to xn as probabilities, or let's make it more simpler. For explaining this, I may draw the matrix as much simpler matrix, feature matrix, as just that whether that feature is present in that document or not. So it gives more simpler representation that instead of having these non-zero numerical values, I am having only binary values here. So that gives more clarity of the problem. So I say that x1, x2, x3 dot 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 xn, and this I say that whether this feature x1 is present in the document, so I give a 1 here. If x2 is not present, I give a 0 here. So similarly 0 1 1, and for this d2 1 1 0. Now so we are actually taking a lot of combinations here for x1, x2 and xn. So this generates large number of parameters. So in this case, if we see the possible values of when x is actually xi is a binary variable, that means it can have only two possible values. Then in case of binary values, we can have x to the power n parameters, right? So where n is the number of features, right? So mod x here is actually the number of values that x can take. So it will be now mod of 2 to the power n, right? So there will be 2 to the power n parameters. So if I take it as x1, x2, x3, so there will be 9 values here. If I take x1, x2, x4, there will be 16 values here, right? And these values will be only for 0 and 1. Similarly, if we change this to much higher values of x, so this will become, if x is able to take more than 2, so it can take 10, 12, 100 and 1000. So this value becomes too large. And if we have suppose 2 number of classes, so this 2 to the power n will be multiplied by 2. So this is quite large, and the number of parameters here is very large, and is very difficult to calculate all these parameters, right? So in order to realize this algorithm, we need to calculate for this binary, and having only x1, x2, x3, x4, we need to calculate 32 parameters. But as n goes large, if n goes 10, so it will be 2 to the power 10 multiplied by 2, so that is again 2048, right? So we don't have very less number of features. We have, in case of a document, a single document may have 100, 200, 300 words present in that. So then now this will become much more higher. So it becomes 2 to the power 100 and into 2, so that is 2 to the power 101. So this is significantly very large number, and it will be impossible to calculate all the parameters for this kind of problem. So this kind of classification setting is actually impractical, and it is not possible to calculate. So that's why we apply some kind of assumption here, so that we are able to realize this problem into actual real kind of problem. So what we do is that we make an assumption. We assume that the words are not related with each other, so they do not affect each other. They are not having any kind of positionally dependence on each other. What is positionally dependence means that if I'm writing some sequence of words, I'm writing bag of words assumption. So this bag is not in any way it is not related to off, and this off is in any way not related to words. So I'm just making this as an assumption, but this is practically or linguistically, this assumption is actually wrong, and the writing of language is based on actually the position of words. I cannot write off bag words, I cannot write words bag off, but I have to only write the correct grammatical sense is that it is bag of words. But I am for just realizing this probability into practical probability, so that I am able to calculate some actual parameters, some low number of parameters. I am making an assumption that these words are in any way not related with each other. So that kind of assumption is called as conditional assumptions. We assume that each features of these probabilities are independent with each other. So when these probabilities become independent, we know when we have this kind of formula p a comma b, and a and b are independent, we just write p of a comma b is equal to p of a dot p of b. Similarly, in case of conditional probability, we can also write p of a comma b given c is equal to p of a given c dot p of b given c, when we assume that these a and b are independent of each other. So since we are applying this independence in conditional probability, we call this as conditional independence. So we assume that all these xi's given Cj are independent of the given class. That means this x1 and x2 are not affecting for a given particular class, right? And that's pretty assumption, but when we apply it into the calculation, we see that this performs quite well, and this works quite well, and we are able to achieve very low number of parameters here. So for each of these formula, we are having only, so x is a single feature, and C is having limited number of classes, so the number of parameters is quite reduced here, because x will be having either 2, 3, 4, or maybe some small number of values, right? So if x is a binary variable, so this is only having 2 values multiplied by 2, so each of these is having 4. So the 4 multiplied by, if I am having 10 values here or 100 values here, that is only 4 into 4 into 4 and so on, right? So that will be 4 to the power again some 10 or 20 or 30 or 40 or 100. So that's again not that much large as compared to previous, right? So in this way we are having a small number of parameters here. So actually these parameters are also calculated simultaneously. So we need to calculate only 4 parameters here, and simultaneously we can calculate only not 4 even, I need to calculate only 2 parameters, because I am having p of 0 given 0, 4 parameters, that's true. It is 4 parameters. So these 4 parameters can be calculated, they will individually, they can be calculated very easily, right? And at the same time we do not require to calculate as in this previous in this kind of previous setting, we are not required to calculate all the parameters. We can just calculate the parameters of those features which are present in that particular document, right? So x1 can be present in, suppose document d1, x1 is present here and x2 is not present, x1 is again, x3 is present here, x2 is not present. So we are only required to calculate those probabilities in which the word is present in the document. So in that way we can quite drastically reduce the number of parameters that are required for calculation. So this kind of Bayes classification is called as naive Bayes classification. So now here we just replace this setting by again p of Cj, that is we have this p of Cj and product of all the probabilities of xi given Cj, and we have this Cj belongs to C and x belongs to x, xi belongs to capital X, that is set of parameters, set of features. So this is now converted into p1. So I can write this like as p of x1 given Cj dot p of x2 given Cj given Cj dot p of x3 given Cj and dot p of x of n given Cj, and this here we have p of Cj. So we multiply all these parameters all together, and we take R max of this and we get the predicted class, right? So we convert a single probability table, that is a large table, the table that we have to generate with the help of n parameters is having mod of x to the power n parameters. Now that has been reduced to a very small number of parameters. So for each individual we need to calculate very small number of parameters. So that is here only we are required to calculate only the single parameter. So this is a single parameter, this is a single parameter, this is a single parameter. We just need to calculate for a given document x1. If it is present, then also we will calculate. If it is absent, then for a given document we need to calculate only one single probability value here. So in that way the number of parameters is reduced here. So how do we apply it into the text classification? We just look into all the words that are present into the document, and then we go one by one and calculate the probabilities. So these, if this is the document, and these are the words written in it, so just we see, go by word and we see that for this word what is the probability, then we go for the next word, what is the probability, then we go for this next word, we calculate what is the probability. So in this way we calculate all the probabilities of those words that are present within the document, right? So this kind of classification is actually the naive Bayes text classification. So we do this for all the classes that are present in the data. So let's see in much more detail how do we realize this formula. So we need to calculate this P of xi given cj for all the words that are present in the document. So how do we calculate this P of xi given cj? So P of cj is actually the probability of class. So it means this is doc count. So that is, doc count is the number of documents for the class cj divided by the total number of documents, and P of wi given cj or P of xi given cj is the count of word that is present with this class divided by the total number of count of that words, where w belongs to vocabulary. So let's again see this visually. So this is the same kind of that bag and ball problem. We are having this class C1 and this is the class C2, and these documents belongs to class C1 and these documents belongs to class C2. So this is D1, D2, D3, D4, and this is also D1, D2, D3, D4. So doc count for class C is equal to Cj. So I calculate the count of all the documents that are present in a class Cj. So this is D5, D6 and D7. So the count of, in this case for C1 is 4, for C is equal to C1 divided by total number of documents is 11, right? And then for C is equal to C2, the document count is 7 and the total number of count of documents is 11. So the probability of Cj for C is equal to 1 is 4 by 11, and probability Cj for class C2 is 7 by 11. So this is the prior probability that we need to calculate initially. So this is the P of Cj. Then we need to calculate the P of xi given Cj, that is count of words in the count of that particular word. So if I give a test document here, this is a new document, and this is di, and I need to find out what is the class for this. So I will be calculating P of di given Cj, that is di given C1, and P of di given C2. In order to calculate P of di given C1, I need to calculate the probabilities and multiply them. So P of W1 for document I given Cj given C1 dot P of W2 for document I given C1, and so on. We need to calculate these probabilities. So this probability is calculated with the help of this formula. So the count of the particular word wi that is present in the document I, we are counting that particular word for the document for the class Cj in the training data. So this is the training data for class C1. So I am counting this particular di is composed of W1, W2 and so on. So if this is W1, so I will be counting the counts. I will be noting down the counts of Wi in class C1 and dividing it by the total number of counts of Wi in with respect to the with respect to all the documents. So the count of wi comma cj. So it is actually the probability of wi given cj. So we given this class, so I'm not dividing it by the whole c1 and c2, but I'm dividing it by the count of all the words present in the class cj. So that is w belongs to v. So this is actually if the count of w1 is equal to w1 comma c1 divided by count of vocabulary that is present in cj, so that is comma c1. So that is equal to w1 count is suppose 20 in this class c1 divided by the total number of words that are present in this is actually suppose 100. So we get the probability as 1 by 5. So similarly we can do the same thing for all the words that are present within the document, and we will be calculating the p of wi given cj. The p of wi is the probability of a word given a class. So I, as stated earlier, that for a conditional probability I just go inside that particular subset and then I calculate the probability and I ignore rest part of the superset. So for cj, if cj is 1, I will be going inside this class c1. I will be just looking into this class c1 part and then calculating the probability of wi. So that will be the probability of wi given cj. So the probability of wi in this subset will be the count of wi divided by total number of words present here, right? Similarly we will do this for all the words that are present in the document di for class c1, and similarly we will do the same thing for another class p of w1i given c2 dot p of w2i given c2 dot 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 for all the words that are present in that document di, and then finally we will multiply both by this p of cj and p of cj. We will get two probabilities, and then we will see according to this formula which value of c is maximizing these probabilities. So if this formula, this probability value, total value is higher, I say that c1 class is the predicted class. If this probability value is higher, then I say that c2 class is the predicted class. So this parameter estimation is actually, again what I repeated just now, is the p of wi given cj is a fraction of times word wi appears among all the words present in the documents of topic cj, right? So we calculate the probability within the class cj, right? And then we calculate some kind of vocabulary, so that by combining all the documents we are able to calculate the probability of each document if required p of di, but we are not calculating it here. Right, so we are just using this one. So the problem with this is maximum likelihood estimation is that, so we are actually calculating the maximum likelihood here. So this is the prior, and this is the likelihood. So we are just trying to maximize this value. So this is the maximum likelihood estimation. So maximizing this value is actually just calculating this value. So maximum likelihood estimation is actually the maximum value that can be obtained of this probability. So this is the maximum likelihood estimate of the word wi. So whenever we don't have any document, any word that is present inside the training document, so I get the count of this word given this class, count of this word given this class as 0, because this word, the count of this word will be 0, right? So we earlier in the previous classes we also studied that whenever the probability of such kind of when the value of such kind of probabilities is 0, we can apply the Laplace smoothing, and then we can calculate the value of probability so that it turns out not to be equal to 0. So just we add +1 here and the +1 here for all the words that are present in the document. So we get the probability as, so we just add the count wherever the count is 0, add 1 here, and we need to add 1 in all the words that are present here. So this summation of WC +1 is actually the counting all the words all together, counting all the words once more in that particular class, right? So in this way we can do the Laplace smoothing. So this is actually the algorithm, naive Bayes, multinomial naive Bayes algorithm written in terms of an algorithm. So we just need to calculate the probabilities of all the CJs. We need to calculate the probability of all the words that are present in the document, and so that we are able to get all the parameters, all these probabilities that are required to predict the class. So we can do it in a kind of loop. We can apply a loop and then we can run it for all the classes. Similarly, we can apply a loop for all the words that are present in the vocabulary, and then we can calculate the probability of all the words. And in this way we can train the naive Bayes algorithm, means that we can calculate all these probability values which are required for predicting the class for the test document. Right, so naive Bayes classifier can be applied to all kinds of text classification problems. It can be applied to sentiment analysis. It can be like applied to any kind of problem. So we can have different kind of features that we can take into consideration while applying the naive Bayes. Not only the words that are present in the document, but we can take some sort of different features. Suppose we can consider email, we can consider URL, we can consider some kind of dictionary. Dictionary means that we are having some previous set of defined words that maybe assume that they are always available in some training document, training data. And then we can also have some kind of network features. So network features depends upon again some kind of intrusion detection problem, in which we have some network parameters as well as we have some kind of the comments that are generated by the user. So in that case, in different kinds of problems, we can have different features that can be applicable, that are applicable to the problem. So this naive Bayes classifier can also make use of those features in addition to the words. So the simple kind of problem is that we are just using only the words with the help of bag of words model, and in order to make the classifier more efficient, we can use some more features, right? So we can also move on to the n-gram model. While using the naive Bayes, we can use the unigram model, that is equivalent to bag of words model. We can use the bigram, we can use the trigram, and so on. So with the help of naive Bayes, we can predict the probability of the words that are present in a particular test sentence. So with the help of this assigning, we assign the probability of each word present in the sentence. We can calculate the probability of the sentence, right? So this is an example here for sentiment analysis. So with the help of unigram model or bag of words model, this is actually a sentence, this I love this fun film, and each word has been calculated this kind of probability of sentiment given class. So finally we can calculate the sentiment given positive. We can also calculate the sentiment given negative with the help of words present in the sentence, right? So if we are using the bigram, then the different probabilities will be of I love and I love and love this and this fun and fun film. So we will be required to calculate these probabilities, and then we will multiply all these probabilities together with the prior probability. We will be getting again the final probability for a given sentiment as positive or negative. So in this way we can apply the bigram also here. So these are the probabilities of the document for positive class. These are the probabilities for that document for the negative class, and we see that the probability of positive sentiment given positive is greater than the probability of sentiment given negative. So we finally obtain that the predicted class is the positive class. So we can have some example here, a very small example here, in which you can understand it very easily. So I am having these 4 documents as the training documents and 1 document as the test document. So in naive Bayes classifier, which is a lazy kind of classifier, we don't actually perform the training, we just calculate the parameters directly during the testing. So such kind of classifiers are called as lazy classifier, which do not actually perform training, which actually calculate the parameters during the testing only. So here the testing documents is Chinese, Tokyo, Japan. So we need to calculate the probability of this document P of test document given these 2 classes. We have 2 classes, P, class C and class J. So I need to calculate P of document test given C, given class is equal to C, and I need to calculate the probability of document of test given class J. I need to calculate these 2 probabilities. I will check whether among these which is the highest probability, I will predict that particular class, right? If this probability is higher, I will predict that the predicted class is C. If this probability is higher, I will predict the predicted class is J. So in order to calculate the probability of P D test given C, I need to again break the document into different words. So what are the different words here? That is Chinese, Tokyo, Japan. So I calculate the P of Chinese given C. Since I am having the counts of Chinese as 3, so I will look it into these in order to calculate this P of Chinese. So I won't calculate it again and again. I will just take it, calculate once and multiply it by 3, right? So in order to calculate P of Chinese given C, I will just consider this C class and just look into this C subset, C class subset, and I will count the number of Chinese present here. So it is 1, 2, 3 and 4. So the count is 4 here, and the total number is 1, 2, 3, 4, 5, 6, 7, 8. Right, so by applying the Laplace smoothing, I add +1 here, and I add plus number of unique words that are present here. I will just make them once more. So this becomes +1 to Chinese, +1 to Beijing, and +1 to Shanghai, +1 to Macau. So in this way, I am having this. I'm calculating. I'm assuming that all these words are present once more, right? So Chinese is present once more, so I get a word 1 for Chinese. I assume that Beijing is present once more, so I again get 1 more count for Beijing, right? So in this way I am having 6 unique words present in the whole training data. So I am assuming the same thing for whole training data, not a particular class. So I will add the value of 6 here in the denominator for the Laplace value, and 1 here in the numerator for the Laplace value. So in this way I get the probability of P of Chinese given C as 6 by 14. So I take finally, which is 3 by 7. So for P of Chinese given 3 by 7, I take this Chinese is actually present 3 times, so I multiply it by 3 times. Similarly, P of Japan given C and Tokyo given C is 1 by 14 and 1 by 14, and this P of 3 by 4 is actually the P of C, that is P of class is equal to C, that is 3 by 4. This the count is 3 here, and the total number of documents for all the classes is 4. So the probability of class C is 3 by 4 and class J is 1 by 4 here, right? So these all probabilities are multiplied all together and we get this final value for class C. So class C given D5 is equal to 0.0003 and probability of J given D5 is 0.0001. So I am seeing that this is the higher probability, so I will finally predict that the predicted class to this document D5 is class C.